I hope everyone's doing well. I am Mr. Ish. Thank you for joining me for this video where we are looking at something very useful. Area of the circle, but that will serve as a model for the point and the theme we're looking at. Parametric curves, the orientation of the curves, and how parametric equations can be brought into area calculations. Everything with regards to integrals. If you start here with a unit circle x comma y, any point on that unit circle, x is always r cosine theta, y is equal to r sine theta, and you know that. The orientation of your parametric curves has very much to do with everything over here. If I'm looking at a representation which just looks like this, a part of a unit circle which is a quarter of a unit circle, and I do the area calculation, I have to just multiply it by 4 and I'll get the full area of a circle, times 2 to capture this part right here, which you know this is an even function, right and left across the y-axis, and then times 2 to capture the lower half, because x squared plus y squared equals r squared, and when you do y is equal to the radical square root r squared minus x squared, this square root eliminates this lower part, hence you have to do a times 2 to capture that part. You're doing a times 2 to capture the counterpart of this, so it makes sense that we can do a times 4. All of that is sensible. How does the orientation of parametric curves play into all of this? It does, because that helps you determine how to set up your integral with respect to dy or with respect to dx. If I'm going from 0 to pi over 2 and theta is my parameter, the third variable, as I have x, y and theta, and I'm going in this direction, counterclockwise direction, the orientation is counterclockwise, then I want to do an area with respect to y, because in this particular case I'll be looking at a right boundary and a left boundary with dy. And why would that be the case? Because as you're starting your curve, your parametric curve, the orientation is going in this direction, you're seeing a right and a left boundary curves. The up and down curves have not established. If you were to do this representation where your orientation is counterclockwise and you ended up doing this with respect to x and 0 pi over 2 yt minus yb dx, you'll end up getting a negative pi r square area. It would be wrong. Where would this negative come from? It would come from right over here. X is equal to r cosine theta dx, the derivative of that is minus r sine theta d theta. You know this d theta can be brought over here, then it would be dx over d theta is equal to minus r sine theta. But I'm just writing the d theta variable with the actual derivative. The derivative of the y expression would be dy is equal to r cosine theta d theta. As I was saying, if you are going to do with respect to x and dx, look what you will be doing, yt, yb, and you know these are going to be square root of r square minus x square. The lower boundary curve y equals 0 is meaningless. Look, you will be bringing the x and the dx, the x and the dx, and there will be a minus which will pop into your integral, and you'll end up with a minus area, and that will be bad. Hence the orientation of the parametric curves are towards counterclockwise. If I do with respect to ay, everything will work out. 0 pi over 2 times 4 right boundary curve, well, this is going to be x equals format, which will be r square minus y square dy. Plug in everything over here. Everything you're looking here, y, dy are all positives. You'll have a positive area develop. 0 pi over 2 square root r square minus y, which is a r square sine square theta. This is my square right here. Dy is an r cosine theta d theta. You just have to compute all of this. From here, using trigonometric identity, simplification, algebra, you'll basically get r cosine theta, which is basically coming from a square root of r square cosine square theta, but it's a perfect square root. It works out very well. You have a 4, 0 pi over 2 r square cosine square theta d theta. R cosine theta from here, r cosine theta, and you're getting this. Bring the r square out, 0 pi over 2, and the power reducing identity, 1 plus cosine 2 theta over 2 d theta. Split everything around the positive sign. You have a 4r square over 2, 0 pi over 2 d theta plus 4r square over 2, 0 pi over 2 cosine 2 theta d theta. You don't even need to look at this, because when you do the u substitution, these will become 0 and pi, the antiderivative will be sine, all of this will zero out. You only focus right here. Here you have a 2r squared, the antiderivative theta, pi over 2 and a 0. Compute this, you'll have a pi r square, but more importantly you'll have a positive pi r square, which is exactly what we want, because we picked the right integral items based on the orientation of our parametric curves. I'm going from 0 to pi over 2. Therefore, I want to do with respect to y, my everything here will be positive and it'll play through with a positive area determination. Now, if I want to do everything here with respect to x, it's fine, you can, but then you understand your orientation must be different. You're going to start here from pi over 2 and then you'll head towards 0, and your orientation will be clockwise, and that will work out. You'll have pi over 2, 0, top boundary minus lower boundary with respect to dx. Here you're going to have a 4 coming out, times 4, pi over 2, 0, top boundary. Well, it's going to be y equals format, r square minus x square in a root, minus a lower boundary, which is x-axis meaningless. Remember, the left boundary curve was your y-axis meaningless. In both instances, these horizontal and the vertical lines are meaningless. Dx. Plug in your substitutions, your parametric substitutions. Pi over 2 to 0, square root r square minus x square. R square minus r square cosine square theta dx. You see you're getting a minus over here, but it'll phase out momentarily. From here, trigonometric identity substitution algebra, you're going to get a r sine theta. This r sine theta will multiply with this, you'll get a minus r square sine square theta. You'll have a 4, bring the minus, bring the r square, you have a pi over 2, 0, sine square theta d theta. You can hit this entire integral with a minus and do the integral limit reversal property and flip your limits around. You have a 4r square, 0, pi over 2, half angle formula or power reducing identity, 1 minus cosine 2 theta over 2 d theta. Bring the 2 out, you'll have a 2r square, separate everything across a minus 0 pi over 2 d theta, and then obviously 2r square, 0 pi over 2 cosine 2 theta d theta. Again, use substitution, limits will change, all of the zeros out. The antiderivative sign and 0 and a pi will be all 0. You focus right here, you know you're going to get a 2r square times a pi over 2 through the antiderivative, which is a theta, which is a positive pi r square, and that's exactly what you want. In the first case, when the orientation is counterclockwise, you have to do the integral with respect to dy. When you're doing a clockwise integration for the area determination, you must do area with respect to dx, and it'll work out in both instances because you paid attention to the parametric equations and the resulting orientation of the curve, or you have to adapt the orientation of curve to make sure you get a positive area determination. That's it for this video. Thank you. Have a good day.